All right. So last time we did a lot with transformations, specifically transformations of our standard base functions or our toolkit functions, whichever way we'd like to say that. And so what we're going to do today is start looking at various specific types of functions. And 1/6 is about absolute value functions. It's basically about the absolute value concept. And then we'll do with inputs, outputs as well. Okay. Now, before we get into the function part of it, I want you to be able to solve absolute value equations. And then we'll solve absolute value inequalities a little bit later. But let's start with equations. So if we have an absolute value equation where our variable is on the inside of an absolute value, let's just make this real simple. Let's say absolute value of x is equal to 5. Well, the absolute value makes everything positive, right? So whatever we stick in here could have either been a positive 5 because the absolute value of 5 is 5, or it could have been a negative 5 since the absolute value of negative 5 is also 5. So if we have an absolute value of something equaling a positive number, then either that something has to be a positive version or that something could have been the negative version of the number. All right. So if we end up with absolute value equaling a positive number, or I should say, or 0, I guess, too, not negative, then that's kind of how we solve it. And beyond this is the basic idea. Once we get into more complicated things, what we're going to do is we're going to utilize that feature. We're going to say we're going to isolate the absolute value part on one side of the equation, get it equal to a number, and then whatever's on that inside, we're going to say could be either the positive version of that or the negative version of that. Okay. Now, here's another thing we have to know about absolute value. If, for instance, the absolute value of x is equal to a -4, or any negative number, then there's no way you can plug in any value, any real number into here, or any complex number. Can't plug in any real or complex number and get out a -4. So then this equation has no solution. So we're going to take advantage of essentially these two properties to solve absolute value equations. All right. So to solve. Oops. Absolute value equations. We want to isolate the absolute value. So get the absolute value on one side. Hopefully it's equal to a positive number. Sometimes it's hard to tell if the number is going to be positive because we'll have variables on this side too. But we isolate that absolute value. And then we set whatever is on the inside equal to the positive version. I'm gonna just write it on the board like that. We say the inside piece has to either be the positive version or the inside piece has to be the negative version. Okay. With equations, it doesn't matter whether to put the negative on the left or the right. Let's say. And then we solve those two equations. And then because of this phenomenon, in more complicated versions of this phenomenon, we should always check our answer. All right, to make sure we don't get something like absolute value equals a negative. Okay. Check. Again, we want to avoid a situation in which we have variables on the left and the right, and you end up putting in a number and you get a negative value over there. Does that make sense? So that's the idea with absolute value equations. Let's go through a couple of versions of these. So we want to solve absolute value of z plus 4 equals 7. Start something like that. Since we have absolute value already isolated, that's good. Now we can set up the two equations. And usually when I set these up, I set them up in the same line. And then I just solve them side by side. So z plus 4 is equal to 7, or z plus 4 is equal to negative 7. In both cases, we'd subtract 4 from both sides. Z is equal to 3 in that case. or z is equal to -11 in that case. Now in this one, again, when I say check your answer, it's gonna be a real quick check usually with me. I just think, well, if I plug in a 3, yeah, I get an absolute value of 7 equals 7, that works. Plug in a -11, -11 plus 4 is -7, inside the absolute value becomes a 7 on the outside, that works. So it's a real quick check of our answer. I'm gonna formally write that down. Okay. Especially on this one where you have absolute value equals a positive number already. That makes sense? So whatever we like to do there. Let's do another similar one. Let's solve 2 times the absolute value of x minus 3 plus 8 is equal to 34. This one we need to do a little bit of work to isolate before we split up our equations into 2. So make sure you get the absolute value by itself. The way you do that in this case is you subtract 8 from both sides. You get 2 times the absolute value of x minus 3 is equal to 26. Then I would divide both sides by 2. That leaves the absolute value of x minus 3 on the left-hand side and a 13 on the right-hand side. Now I split the equations in 2. The x minus 3 could have either been a positive 13 or that x minus 3 could have been a negative 13. In both equations, to solve for x, we just add 3 to both sides. In the left equation, you get x equals 16. In the right equation, you get x is equal to negative 10. And then you can check your answer by saying, well, what would happen if I plugged in 16? 16 minus 3 is 13. Absolute value of x, look at 13. 2 times 13 is 26, plus 8 is 34. We're good. Negative 10. Negative 10 minus 3 is a negative 13 inside the absolute value. When you take the absolute value, that gives you a positive 13 times 2 plus 8. That gives you 34. All right. So it's a quick check of those answers. Let's do a couple others. if you were given something like absolute value of x plus 8 plus 10 is equal to 3, the first thing you would do is try to isolate the absolute value. Which gives you x plus 8 is equal to -7. Now, at this point, if you wanted to say, oh, I can see that the answers aren't going to give me any solution, you can, right? We have absolute value of numbers equaling a negative. And therefore, we could stop right there and say, that's never going to give me a solution. If you did happen to go through the procedure of using x plus 8 is equal to the -7, or x plus 8 is negative of -7, +7. You could have done that as well, and then solved. Gotten that x equals -15, and then gotten an x is equal to -1. And then what you would have done when you check your versions, the x equals -15 when you plug it in, would have given you a +7 is equal to a -7. And when you plug in a -1, you get a +7 equal to a -7. So neither of those would have worked when you checked your answer. And so you would have been left with no solution. I think in Moodle, if you have no solution, you're supposed to write D&E for does not exist. And in Moodle, when you have two solutions like this, it'll say to either write the smaller one first or the larger one first, but it'll indicate which one to write first and which one to write second. That makes sense? So write the larger answer first, so you'd write the 16 first, and then smaller answer second, you'd write the -10 second. That work? Obviously, things get more and less complicated. We're not going to really go into the more complicated versions where we have variables inside and outside the absolute value right now. Okay, so we won't do that right now. We may come back to that later on in the semester though. But that's the basics of solving absolute value equations when we can, when we can't. So we're always isolating the absolute value and then saying absolute value is equal to a number when the thing inside of the absolute value is either the positive version of that number or the negative version of that number. Okay. So that's the basics of it. Now, we can also do the same thing with inequalities. So with absolute value, inequalities, we can solve in very, very similar ways. So let's say I have the absolute value of z minus 2 is less than I'll just do 8. So we're going to solve that. And we're also going to solve z minus 2 and absolute values is greater than 8. Now there's a trick that I'm going to do, not trick. Trick's probably the wrong word. But there's a technique that I'm going to do where I'm only going to be focused on sort of the important values of when is this absolute value equal to 8. So I'm going to start by solving the exact same equation with an equal sign in it. Notice for both of these, it's going to be the same one. And so the z minus 2, just like we did just a minute ago, is going to be equal to positive 8 or negative 8. We can add 2 to both sides. And in both cases, we'd say if this was an equal sign, our answers would be z equals 10 and z equals negative 6. We're okay with that. Here's what I like to do. Z equals 10 and z equals negative 6. I think about on a number line. These are sort of the cutoff values for sections of the number line that would work in my original equation. Okay with that? So in other words, all numbers in this section are either going to all work or all not work in this original equation. All of the numbers in this section are either going to work or not work. And all of the numbers in this section are either going to work or not work. Okay. So if I just pick out a number, let's pick out, for instance, negative 8 and plug it in here. Negative 8 minus 2 is negative 10. If I do absolute value of that, I get positive 10, which is not less than 8, is it? So negative 8 did not work. That means no numbers in here in this section are going to be solutions. So there's no solutions in this section. The same thing is true in this section. If I plug in a 12, 12 minus 2 is 10. 10 is not less than 8. There's going to be no solutions in that section either. If I plug in something in the middle section, let's say I plug in the number 4. 4 minus 2 is 2. That is less than 8. So all of my solutions are going to be in that middle section. And that's just through trial and error plugging things in. Now, we will start learning that when you have absolute value less than a number, you always end up in the middle section. And we'll start learning that, well, if you start plugging in numbers like negative 10, it turns out you get a solution here for this one. You don't get solutions in the middle, and you get solutions on the outside. That makes sense? Now, a lot of times what happens is we will draw on the number line our solution. If you're drawing your number line solution, then what you do is you say, since the solutions are in the middle, I'm going to put circles around negative 6 and 10. And since the solutions are in the middle, I'm going to shade that middle region. Also, could I have plugged in a negative 6? No, because negative 6 would have given me an equal sign, and equal is not allowed here. Only less than is allowed. If this were less than or equal to, then I could have plugged in a negative 6. So when you have just less than, you use what we call open circles. Circles where it's not filled in. The same thing is true, obviously, for 10. There's no equal sign, so we use open circles. Now, algebraically, I want you to notice something. Algebraically, the z needed to be bigger than negative 6, and our z needed to be less than 10. So our z needed to be between negative 6 and 10. That means our z needed to be bigger than negative 6, but less than 10. So when people talk about the solutions here, you could either write your solution like on a number line, like this, or say that it's all numbers which are bigger than negative 6 and less than 10. So that's the algebraic version of the solution. This is the number line version of the solution. I'll show you a way to get the algebraic solution without having to like think through it and look on the number line in just a moment. Okay. First, let's do this one. Solutions, once again, we do not have the equality. So we draw open circle at -6, open circle at 10, and then we shade on the outsides this time because the solutions are anything that's smaller than -6 and anything that's bigger than 10. Algebraically, this means that our z needed to be smaller than -6, or our z needed to be bigger than 10. That makes sense. Now, let me show you another sort of option for solving these. Everybody okay with this so far? Okay, let me show you another option for solving where you don't use the equality. This one's a little bit maybe more confusing, but let me take a stab at this one. Let's say I want to solve something like absolute value of 2x plus 7 is greater than or equal to 35. Now, in the last examples, we said, well, let's just pretend that's an equal sign and get the two cutoff values. Okay. If you think about how the negative, positive versions of this work, if this were positive, then we could have just dropped the absolute value sign and solved this inequality as is. So if the thing inside were positive, we could have just said 2x plus 7 is greater than or equal to 35. In the case that the inside was positive. Now, what if the inside were negative? This might be a hard concept, but I'll erase this in a moment. So this is kind of off to the side scratch work. Let's say we had a negative value. In order for the absolute value of something that is a negative number to be bigger than 35, it needs to be to the left of negative 35. Does that make sense? If it were negative. So what does that mean? that means whatever this value is, that has to be to the left of negative 35. So if the inside is negative, then this number, 2x plus 7, needs to be smaller than negative 35 for that absolute value equation to be true. Does that make sense? So if you wanted to go get the algebraic answers without having to think through on a number line, you can do so by saying, well, first off, you'd isolate the absolute value. You always want to isolate the absolute value. That's done on these two. So isolate the absolute value, then say, well, if the absolute value is positive, I keep the sign in the same direction. But if the thing inside the absolute value happened to be the negative version, I need to flip the sign. All right. Because of the way the number line works. So if the inside's negative, we flip the sign. If the inside is positive, we get the same sign. Meaning greater than or equal to, less than or equal to, greater than or less than. And now we can solve this normally. If you remember how to solve inequalities, when you subtract from both sides, the sign does not change. When you divide both sides by a positive number, the sign also does not change. Same thing over here. When you add or subtract a number to both sides, the sign does not change. When you divide by a positive, the sign also does not change. And I get that. Now, the advantage of doing it this way is immediately I know the algebraic answer, but also if I do it this way, I don't have to really test which sections work. This already tells me which sections work. The section that is above or equal to 14 is going to work. Now, above 14 means I'm pointing to the right. Since we have the equal sign, we actually fill in that dot. And the section where the numbers are less than or equal to negative 21 also work. Again, since we have the equal sign, we fill in the dot. Since it's less than, we point to the left. Notice once again, here we had absolute value greater than or equal to a number. We got the sections that were pointing both on the outside. Any questions about this technique? So use whichever technique you like. Use like pretending the equal sign and then just checking where the solutions are. If you like that one better, use that one. If you like the one where I say, well, if the inside is positive, you keep the sign the same. And when the inside is negative, you flip the sign, use the negative number. Whichever one of those you like, just keep using. Okay. We've done a couple where we've had pointed on the outside. We could have a couple where we're pointing on the inside. Let me do one more example of solving an absolute value inequality. So let's solve this one. Let's solve absolute value of 7 minus x let's do greater than or equal to 3. I want you to go ahead and try this on your own. All right, so I think since I've done 2 with the equal thing and then checking, I think I'll do this one again. All right, so if the inside piece is positive, I keep the sign the same direction. And I say, well, that means x minus x, 7 minus x, excuse me, is greater than or equal to 3. If the inside is negative, then I flip the sign direction. And I use a -3. So I say 7 minus x is less than or equal to -3. In this case, if I was solving for x, I'd have to subtract 7 from both sides. In both cases. that would give me a negative x greater than or equal to -4, and a negative x less than or equal to -10. Now, in this case, my coefficient in front of the x is negative. So I have to be really careful about this. When I divide by that coefficient, which is -1, I have to flip the sign. That's opposite of over here because I was dividing by a positive number. When you divide both sides by a positive number, you keep the sign the same. When you divide by a negative, whenever you divide by a negative, you have to flip the direction of that sign. You guys remember that back in the day? So x is less than or equal to 4. And on the other one, since we divided by a negative, I ended up with x greater than or equal to a 10. So that's my algebraic solution. X is greater than or equal to, so you gotta say greater than or equal to 10, less than or equal to 4. And you'll notice if I draw that out, less than or equal to 4, since we have the equal, I shade in the circle. Less than or equal, pointing to the left. Greater than or equal to 10, shade that circle in, pointing to the right. Once again, see how my absolute value was greater than a number? And we got the outside versions. Any questions about solving? So that's the thing, if you want to use the equal sign, you would have just found 4 and 10, and then you'd have to figure out which sections are the good ones and which sections are the bad ones. And if you want to use the less than and greater than symbols while solving, that's fine. You just have to remember the rules of how to solve an inequality. That makes sense. So either way, I'm fine. If you want to use the equal sign and then just check the 3 sections, good to go. If you want to use inequalities and then do what I just did in these last 2, that's good to go too. All right, so either way is fine. And there's probably other ways as well. Okay. All right, so we've solved enough inequalities in absolute values, and we've solved enough equations in absolute values to go on to the main part of 1.6, and that is, what are some features of absolute value functions? So if I have an absolute value function, what are some features? Now, we've already done transformations back in the previous section, 1.5. All right, remember that? So we've already done transformations. So we know that our base function graphically is gonna look like a V. And we know that the bottom of this V, this point of our base function is 0, 0. So if I want to shift this around, left, right, up, and down, we've already done that. So we've already kind of graphed it and shifted and done all that stuff. All right, reflected it, flipped it by throwing in a negative on the outside. All that kind of good stuff. So we already know that. So now what we're going to do is we're going to say, well, if I have an absolute value function, can I find certain things? We already know, again, the tip of the V from transformation, that's shift left and right. But also, we're going to find in this section the X and Y intercepts if they exist. Right, know what I mean by X and Y intercepts? X intercepts the thing that hits the X axis, Y intercepts the point that hits the Y axis. So for instance, if we take our base function and we shift it right and down, then this absolute value function is going to hit the X axis in 2 spots. And it's going to hit the Y axis in 1 spot. I'm going to erase my base function here. So that point where our function hits the x-axis is called the x-intercept. In this case, the way I drew it, this one has 2 x-intercepts and 1 y-intercept. Now, if I gave you a different absolute value function, that might not be true. So not every absolute value function is going to have 2 x-intercepts and 1 y-intercept. If I had shifted, let's say, to the left and up, notice that version, there's no x-intercepts. It will have a y-intercept. Because it will hit the y-axis at one point. So notice what we're getting at is all these absolute value functions are going to have 1 y-intercept. But some of the absolute value functions will have no x-intercept. Some of the absolute value functions will have 2 x-intercepts. And some of them will have 1. And that 1, just like on our base absolute value function will just hit the x-axis and go right back up. It'll be the tip. Does that make sense? So if we take our absolute value function reflected across the x-axis, move it over. I get that. I get my x-intercept in one spot, and then eventually it'll hit a y-intercept over here. Draw it very well. So you can have no x-intercepts, two x-intercepts, or one x-intercept in absolute value functions. Okay, but every absolute value function is going to have a y-intercept. So that's why I say if they exist. That's a long-winded version. Now, I want to also point out that x-intercepts always have the form of some x value in the x spot and 0 in the y spot. Because they always hit the x-axis, hitting the x-axis means you have a 0 in the y value. Okay. Whatever it is. And it's exactly the reverse with y-intercepts. Y-intercepts always have the form 0 in the x value, and then we get some y value. So if we're looking for x-intercepts, what we do is we just plug in 0 for y and see what value of x I get or can get. If I'm looking for y-intercepts, I plug in 0 for x, figure out what value of y I get. So let me write that down. To find x-intercepts, plug in 0 for the y value. To find y-intercepts, plug in 0 for the x value. And so if we know transformations and how those work, which we did in 1.5, and we know how to find our x and y intercepts, then we can basically find what, for this class, we're going to be looking for absolute value functions. Okay, how are they shifted from the base function? And then what are the x and y intercepts? Okay, so since we already did the shifting stuff last class period that we were in here, we'll do the x and y intercepts now. And by the way, this works not just for absolute value functions. Any functions that we want, we can find x and y intercepts this way. Okay, so this is not unique to absolute value functions. And next week, we'll come in here and we'll look at some other types of functions. We'll say, what are the x and y intercepts? And we'll find the x-intercepts by plugging in 0 for y. Find the y-intercepts by plugging in 0 for x. Okay. All right. So let's find, if they exist, the x and y intercepts for the following absolute value function. F of x is equal to the absolute value of x minus 3 minus 4. I'll find the y-intercept first. Now, by the way, all functions can only have one y-intercept. Because if you have two y-intercepts, then you failed the vertical line test. You're not a function anymore. So when I say y-intercepts, technically you can only find one if it's a function. So let's do the y-intercept first. Basically, I just plug in 0 for x and see what I get. Absolute value of 0 minus 3 is a 3. Minus 4 gives me a negative 1. Now the y-intercept, therefore, is the point 0, negative 1. Now the x-intercept, we got to plug in 0 for y. Now when we say plug in 0 for y, we hopefully all know now that f of x is a stand-in for a y value, right? An output value. So we plug in 0 for the f of x. And then notice what we're doing. We're essentially just solving an absolute value equation like we've done, I don't know how many times now, but quite a few times now. So I would add 4 to both sides. That gives me 4 is equal to the absolute value of x minus 3. Since this is an equal sign, absolute value is equal to positive, I can solve this one, right? So I can say either the absolute value of x minus 3, the thing inside is either positive, meaning x minus 3 itself is 4, or x minus 3 is a negative 4. And if you are more comfortable putting the x minus 3 on the left-hand side or the right-hand side, it doesn't matter. You want to do x minus 3 is equal to 4 instead of 4 equal x minus 3. You can go either way. But in both cases, you'd add 3 to both sides. Over here, I got an x value of 7. Over here, I get an x value of negative 1. That means I have 2 different x-intercepts. one which has x value of 7, y value of 0, and the other which has x value of -1 and y value of 0. Is that okay? So this one had 2 x-intercepts. Any questions about that? Pretty straightforward. Finding the y-intercepts, plug in 0 for x. Finding the x-intercepts, plug in 0 for y. When you plug in 0 for y, you're going to end up with an absolute value equation. And just so that we're all on the same page, if your absolute value equation ends up as absolute value of x plus 1 is equal to -5, guess what's going to happen? There's going to be no solution, and therefore there's no x-intercepts, right? That's going to yield the no x-intercepts version. I want you to do one more where we find the x and y intercepts. Let's take another function, let's call it g of x is equal to 2 times the quantity x plus 4 minus 18. Go ahead and try to find the y-intercept and the x-intercepts for that one, if they exist. All right, so let me go through this. This will be the last one I do in this section. So to find my y-intercept, I'm going to replace the x value with the 0. So we end up with 2 times 0 plus 4 inside of absolute values. minus 18. And you take 2 times 4, and then subtract 18, you get a negative 10, should be a negative 10. So the y-intercept is the point 0, negative 10. The x-intercept happens when the absolute, or excuse me, when the y value is 0. So plug in y equals 0. And that gives you that your absolute value expression is equal to 0. And then we can solve this. First thing we want to do is isolate the absolute value. In this case, I have to add 18 and then divide by 2. I would get 9 equals absolute value of x plus 4. And then that means either the 9 is x plus 4, or x plus 4 is equal to 9, or x plus 4 is equal to negative 9. And again, it doesn't matter whether you write the x plus 4 on the left side and the 9 on the right, or vice versa. Subtracting 4 from both sides of each equation gives you, over here, x is equal to 5, or 5 is equal to x, however to write it. Or x is equal to negative 13. So we get the x-intercepts. We have, again, 2 of them. One is 5, 0. The other is negative 13, 0. And in Moodle, it'll say, write the one with the largest number first, or the one with the smaller number first. I forget which way it does, but it'll specifically state, write the larger number first, smaller number second. And if you swap it, it'll give you a wrong, say, oh, this is not right, because of the order. So just read that carefully in Moodle, and it's pretty straightforward and obvious. But there you go. Any questions about finding x and y-intercepts on the absolute value functions? Again, we put in most of the work earlier, being able to solve absolute value equations. All right. So now we're going to do the last part of chapter 1. And because these 2 sections are connected, we're going to do them kind of same time-ish, all right? They're very, very much connected. 1-4 is operations on functions. And 1-7 is the function's inverse. An inverse is an operation I can do on a function. And we'll talk about what that actually means here in a little bit. Now, anytime I have a couple of different functions, I can do our basic algebraic operations. So when I say operations on functions, one such operation are the algebraic ones. Think add, subtract, multiply. And divide. Okay. And if I have two functions, I'll make them fairly straightforward. Let's say f of x is equal to 2x minus 5, and g of x is equal to x squared plus 3x minus 1. If I said I'm going to add these two functions, f plus g, what I'm really telling you is I'm going to add the output of those two functions together. So if I said, what is f of x plus g of x? Now there's two notations that you could see, either f plus g. Some people would say just f plus g equals. You see f plus g sometimes, or this notation, f plus g of x, to show that when you add two functions, you still get a function. That means the same thing as f of x plus g of x, which is essentially just taking the output of 2x minus 5 and adding an output of x squared plus 3x minus 1. When you add these two, it's just adding polynomials, so adding like terms. X squared doesn't have another like term. 2x and 3x are like terms, so you get 5x. Minus 5 and minus 1 are like terms, so you get minus 6. So f plus g is just the result when you add the two outputs. Now, oftentimes, you may be asked to say, what is the result when we add two functions with a specific input value? So in other words, what's f plus g of 2, for instance? And you can do this one of two ways. If you've already added f plus g together, and now you have a specific function output, f plus g of 2 can be calculated by just plugging in the 2 into my new combined output. On the other hand, you could have also plugged in 2 in for my original f, and then 2 into my original g, and then added those results together. You're going to get the same thing. In the end. And you can kind of see be that if you're gonna be plugging in lots and lots of inputs, this is probably gonna be an easier one to plug into if you're plugging in lots and lots of different inputs. So let me calculate that. 14 minus 6, I believe you get an 8 here. And then this gives you -1. This gives you a 9. -1 plus 9, also 8. Is that okay? So addition works that way, where you can either, in general, add 2 functions and get a new function, or you can add the 2 functions with a specific value. And again, that could have been accomplished either of these 2 ways. Plug in that specific value into the f, and then also the g, or plug in that specific value into the new combined function, whichever one you like. So that's the basics of it. All right. Now, when you add, that's pretty straightforward. Do it that way. Notice that when you add 2 functions, you get back a function. If you subtract, I'll move over here, and do f minus g, you do have to be careful about order. And specifically, when you subtract g, you need to make sure you subtract the entire thing. So my function g had multiple terms. So that subtract symbol, subtraction has to distribute into each and every term. So in other words, make sure you treat this entire thing as your g as one component, right? All 3 terms are the function. So when you do f minus g, you get -x squared minus 1x minus 4. And if you want to plug in 2 or plug in 5 or plug in 3 or plug in -80, you could have done that. Okay. Plug in whatever value you want. When you multiply, now this is where we're going to get into the tricky thing. You can either write f times g just right next to each other, or you can write a multiplication symbol. If you write a multiplication symbol in, make sure it's a small little dot or an X. Okay. Because we're going to have another symbol that's an open circle that means something else, means composition. Make sure that when you write it, you can see that that's a multiplication symbol and not a composition symbol, which we'll see later. Okay, just a moment. But f times g, it's simply your expression for f multiplied times your expression for g. And if you were going to make that into 1 or try to simplify, you'd have to distribute the 2x. Hopefully we know how to multiply polynomials. And then distribute the -5. and then you combine like terms, right, to simplify. So f times g is equal to 2x to the third plus 1x squared, or just x squared, minus 17x plus 5 when I simplify that. And just so you know, on Moodle, when it asks you for that, it's just gonna have the coefficients as a blank box in front of x to the third, plus coefficient in front of a blank box in front of x squared. So you're just filling in the 2, the 1, the negative 17, and 5. We okay with that? So it'll look similar to that in Moodle, where you just fill in the coefficients. And then lastly, if you were dividing, let's say we took f over g. That's pretty obvious. We just take the expression in f, divide by the expression for g. Now it's not going to be able to be simplified, so we'll just leave it as is. And in any of these, if you wanted to plug in numbers, just plug in numbers. Now, just an aside, very quick aside, you're not going to be tested on this. If we talk about the domain of when you add two functions, it's going to be the same as the domain of the original two functions. So if the original two functions domains are all real numbers, adding, subtracting, multiplying give you still a domain of all real numbers, like this one did. If there was a problematic spot, you'd have to avoid that problematic spot when you added or subtracted or multiplied as well. Does that make sense? Dividing sometimes can give us new problematic spots because now we might be dividing by 0. So it might be given some new problem spots in our domain. But when you add, subtract, or multiply, you're not given any new problem spots. So the domains are just the intersection of the domains of the original two functions. Any questions about add, subtract, multiply, divide functions? Pretty commonsensical. Now here's the main portion of 1-4. The main portion of 1-4 is the operation of composition. So composition of functions. And I'm going to start with the notation. It looks like f of g, where there's this little o here that's in the middle. It's not fog, it's just f, little o in the middle, g. It's almost like the multiplication symbol, but it's an open dot. That's a little bit bigger. That's why I said be careful with the multiplication symbol. So f of g of x. And what that means is you are going to take the input into f as whatever you got out as your output of g. So we input G, we input the output of G into F. So here's what we do. We start with an X. We apply some function to that X. We'll call it G first. We get a specific output. That output is going to be G of X, whatever number that happens to be. So that's what happens with a function, right? And then after that, we apply a new function, F, and we're going to get another output. Whatever we got out, of G, input into our F, gives us another output. That's what composition of functions means. We apply one, we get a number, and then we apply the next one to that number we just got. So let's do this numerically and algebraically. Let's say we want G of X to be 4x plus 1 and F of X to be negative 1x plus 8. Let's do this numerically first. Let's say we want to do F of G and input the number 3. So what you would do is you would say that means I want to plug the number 3 first into my function G, always the near one. Okay. You plug it in first to the near function. So G in this case. Now when you input 3 into G, that is just this expression. So you're going to get 4 times 3 plus 1. That means the input, when you plug in 3 into here, gives you an output of 13. You okay with that? So you're going to get 13 out. And then you're going to plug that 13 into the input for F. So if you compose F with G of 3, you get out a negative 5. Now, before we move on, I just want you to see what happens if you went the other way. If we went G of F of 3. In this case, you'd have to plug in the 3 into your F, because that's the nearer one. Negative 1 times 3 plus 8 is what you have to do first. That gives you out a 5. And when you plug the 5 into your G, 4 times 5 plus 1 gives you 21. So the order of composition is very important. Which one you plug in first, which one you plug in second. So you have to be very, very careful about the order of composition. So that's what happens numerically. You can just plug in and trace through. Now, you can also do this algebraically too with a variable plug-in. So in other words, algebraically, I could ask, what is f of g of x? Or some people would just write that as what is f of g without writing an x. Is that okay? Just to save time on writing. It's kind of a trick. If it's a variable that's x, say write time on writing, we just don't write it. Right, f of g. That's shorthand for this. Same notation as that. So what you would do is you would take your function g of x, which is the expression 4x plus 1. And plug it in for f. So every time we see an x here, we replace it with 4x plus 1. Can we do that again? If f of a certain number is negative 1x plus 8, negative 1 times that number plus 8, and I said, well, what's f of z? You'd say, well, it's negative 1 times whatever the number z is plus 8. And if I said, well, what is f of z minus, no, let's do plus, z plus 30, you'd say, well, it's negative 1 times whatever I plugged in plus 8. And this thing can get as complicated or as easy as we want. So what we're going to do is we're going to take negative 1 times the expression 4x plus 1, and then add 8. Are you okay with that? And then on Moodle, you probably simplify and then write the coefficients again, kind of thing. So I'll simplify this. Negative 4x minus 1 plus 8. So that tells me f of g is equal to negative 4x plus 7 when I simplify it. So that's composition of functions, algebraic. Let's do the other way, just so we have this. What if I go g of f? So in for the input into g, I'm going to plug in f of x, which is the expression negative 1x plus 8. Just like I did earlier, I say, well, G, whenever I plug in a number, I take 4 times that number plus 1. Now my number is an ugly thing, but still I can do 4 times that ugly thing. Plus 1. So 4 times my variable plus 1. My variable happens to be negative 1x plus 8 this time. 4 times my variable plus 1. When I simplify that, I get negative 4x plus 33. It looks like 4 times 8 plus 1 is 33. Notice once again, order makes these two things not the same. Now, once you've done that algebraically for a couple of these, obviously if we get really complicated functions, the algebra is more cumbersome. I'm not going to give you really cumbersome algebra, but you can see what's going on there. Let's do another. Let's take g of x is equal to x squared plus 3, and f of x is equal to x plus 4. And let's algebraically do f of g. Go ahead and try that on your own. And if you have a minute, you can try the other one too. I'll do the other one as well. G of f. All right, so let me do the f of g. That's the one I want you to be able to do right now. F of g, we plug in the g of x into the f. And the g of x is x squared plus 3. So we plug that in. Our f of x is variable plus 4. Our variable now is x squared plus 3. So when you simplify that, f of g is equal to x squared plus 7. Simplify. By the way, if Moodle has blank x squared plus blank x plus blank, and you're supposed to write your answer in, you would write, there's a coefficient of 1 in front of x squared. There's no x term, so we put a 0 there. And the constant is a 7, so you put a 7 there. Right? So if you don't have a term, you put 0 as the coefficient. That makes sense? The other way around, where we go g of f of x, or g composed with f of x, means that we plug in the variable x plus 4 into g. Well, usually I take my variable squared plus 3, so I'm going to take my x plus 4, square it, and add 3. That might take just a minute of algebra. X squared plus 4x plus another 4x plus 16, when I multiply that out, and then plus 3. We've multiplied polynomials before in here, so I think that should be all right. So x squared plus 8x plus 19, it looks like, is the final answer. Any questions about function composition? Now, there's one other thing I want to mention. And what was that caps? Caps lock. Oh, there's not sharing, because not sharing. Let's do it that way. Okay. Let's say I want to do something graphically. And let's say I don't even know what the functions are supposed to be, but I have the graph of the two functions. We'll call the line my f of x, and we'll call the parabola my g of x. Okay. If I said, what is f of g of 2, for instance? So we do graphically f of g of 2. In the same way I numerically traced this, if I said, let's plug in a 2 into my g function, you'd say, well, plugging in a 2 gives me an output of 0. And then I'd say, well, now let's take that output of 0 and plug it in as the input for my f function. Does that make sense? So if I said, let's start with the parabola, plug in an input of 2, and then plug in that into my line, you'd say, well, an input of 2 gives you an output of 0, gives you an input of 0 on the next one, which gives you an output of -1. So f of g of 2 would be -1. Do you follow that? Let's do the same thing, f of g of 1. Well, if I input a 1 into my parabola, I get output of -3. And then I go an input of -3. I have to scroll out a little bit. Onto my line, which would give me an output of -7. So f of g of 1, put an input of 1, gives you -3. Input a -3 into the other one, gives you an output of -7. So you can do this with graphs, just like we could with numerically plugging things in too. Just think inputs and outputs. Okay. Okay. Oh, thought I did that right. There we go. So that is all of my operations on functions. Now we're going to talk about function inverses. Okay. And here's what I'll do. To show off a function inverse. Let's say I wanted to compose G and F. So I go F composed with G in this case. And in this case, my F is square root of x minus 3, and my G is x squared plus 3. Now here's where it gets tricky. If I take a square root of x squared, what do I get? I told you if you had to answer that.
Just x.
Just x, kind of. Kind of. If x were negative, you wouldn't get just x, you'd get the opposite of x. Does that make sense? So here's the tricky part. When you take square root of x minus 3 and you're composing that with x squared plus 3, you get back your x when the domain is right. You get back x as long as x is greater than or equal to 0. So this is trying to demonstrate two things simultaneously. First thing, when you compose two functions, you get back x. Now, if you think about what happens if you get back to x, what have you done? You've taken in an x and you've gotten back an x. You've gotten basically an identity. Your input is the exact same as your output. So your input, you go through this big process and you get an output. That's the identity function, is when you input an x and you get out an x. Right? So first, the identity function. is one where you input an X and the output is that very same value. So it's a function where you input an X, you get out an X. Okay. Everybody get that? So what is a function inverse? A function inverse is a function, and we denote it with an f to the -1. Function inverse, or I should say the inverse of f. Maybe let me rewrite this. I'm sorry. The inverse of f. If that makes sense. Inverse of f of x is a function such that when you compose f with f inverse, you get back the identity function, or you just get back an x. And you also need the other way. So if you compose it the other way, you get back the identity function, or you get back an x. So a function inverse is one where you compose it and you get back x. Now, these two functions that I just gave you are inverses as long as we're on this domain. So f and g here are inverses on this particular domain. Okay. Now we're not gonna ultra focus on the domains. We're just gonna say are f and g inverses on a correct domain. I'm not gonna get into the weeds of how that works. In fact, you actually may need the f and g are inverses on the domain x greater than 0 when we're composing this way. But when you're composing the other way, you might need x greater than 3. Does that make sense? Maybe it's actually x greater than or equal to 3 because you want to plug in numbers which are 3 or more initially in here. Is that okay? So on some particular domain, they're inverses of each other. Inverse is going to be the identity function. Okay with that? So you can check inverses algebraically by just composing them if we want. But that's not going to be the main push for section 1.7. I do this? If you're ever asked, does this function have an inverse over the real numbers? What you need to do is check if that function is what's called one-to-one. A function is 1 to 1 let's just say over the real numbers. If we have two outputs that are the same, causes the two inputs to be the same as well. That's a fancy way of saying that to be a function, we have to satisfy a vertical line test. To be one-to-one, we also have to satisfy a horizontal line test. And I said over the domain of all real numbers, but you can do this over any domain you'd like. So for instance, if you look at this line, this red line, there's no two outputs on the same horizontal line. So the red would be one-to-one. So a line is one-to-one. But a parabola is not one-to-one. Because as you notice, hopefully, you take a number like -3.5 and another point like 3.5. Those have the same output of 5, but there's two different ways to get there. So that does not satisfy the horizontal line test. Do you follow? And it turns out for a function to have an inverse over the real numbers, it has to be one-to-one. Okay. Now, we're not, again, going to focus too much on the domain. So we're going to say, yeah, these are inverses as long as we restrict the domain to the place we like. Okay. But I'll write that down here. To have an inverse over a domain, the function must be one-to-one on that domain. And what we do is we say, well, yeah, we can always just restrict our function to a particular domain, to a particular small enough domain, so that we get an inverse over the small enough domain. That makes sense? And generally we assume domains are good. Now, here's the question. How do we find inverses? How to find inverses? I'm gonna go back to the drawing I had earlier. We started with an X. We applied a function G. We got out something which was an output, which is a Y value. And then we applied a function F. And if these two are inverses, we get back out an X, right? If they're inverses. Notice what's happening. On one way, we're going from an X to a Y. On the second one, we go from a Y to an X. So to find inverses, what we're going to do is we're going to switch the role of X and Y and then solve for X. Switch roles of X and Y. Solve for, I should say solve for Y and do X. Okay. Solve to get Y equals. So let me give you an example. Let's find the inverse of f of X equaling X minus 2 to the third plus A. So I swap the role of X and Y. This is like Y equals that. So I'm going to say, well, let's switch the output to an X and the input to a Y. Does that make sense? We're going to switch the output. Originally, we had input of X and output of Y. Now we want input of Y and output of X. Look at that. And this thing I can solve. I can solve and get Y equals. How would I do that? Well, in this case, I subtract 8. That would give me X minus 8 is equal to Y minus 2 to the third. How do I get rid of a third power? I take a third root. So let's take a third root of both sides. Now the nice thing is third roots are 1, so we'll work on anything. But I get a third root of X minus 8 equals Y minus 2. When I add 2 to both sides, now be careful, when you add 2 to both sides, don't add the 2 inside of the root, you gotta add the 2 on the outside. So you get, I'm gonna switch the order. You get Y equals cube root, and inside the cube root is an X minus 8. And outside that cube root is a +2. This means that the inverse function of f is in fact the cube root of x minus 8 plus 2. That make sense? So that's how we find inverses. We just simply switch the roles of x and y and then solve. Now there's different techniques for solving. Obviously certain equations are easier to solve for than others. This one, we took a cube root because we had a third power. You can imagine if we had a squared power, we take a square root. To undo a cube root, we cube things. To undo a square root, we'd square things. Let me do one other. I'll try and do this very quickly because this is one that sometimes people struggle with. Let's find the inverse. I'll call this one G. G of x is equal to 2x minus 1 over 3x plus 6. Okay. So we want to swap x's and y's. I take x equals 2 times y minus 1 divided by 3 times y plus 6. I would multiply the 3y plus 6 on both sides. That would get rid of my denominator, or you can think of this as cross multiplying. Now, what you would do is you would get all of your y terms on one side and all of your terms without your y's on the other. So I would subtract 2y from both sides. And I would subtract 6x from both sides. That would give me 3xy minus 2y equals minus 6x minus 1. Then I could factor a y from the left-hand side, since every term has a y in it. I'd factor that y out. And then what I would do is I would divide both sides by 3x minus 2. Which gives me a y equals negative 6x minus 1 over 3x minus 2, which means that my inverse function of g is exactly that. Negative 6x minus 1 over 3x minus 2. So I just want to give you that trick because sometimes people forget how to solve for y in that case. Get all the y's over, factor out y, divide by whatever's left. But it's the same thing over and over and over. If ever you want to find an inverse, you want to swap x and y values and then solve. Now notice when I solve, I kind of ignored the problem spots. There's going to be a problem spot when we're dividing by 0 here. There's going to be a problem spot when I'm dividing by 0 here. So when x is -2 up there, when x is 2/3 down there. So we do have to worry about our domain, but just assume you're working with valid domains, all right, when you're doing this. So we assume we're working with valid domains. In the back of our minds, we know we have to be a little bit careful about what we plug in. Okay. All right, well, you have all the tools you need to do all of the problems in 1.4 and 1.7. If you do have any questions or if you need extra time, email me on that. And then we'll start up on chapter 2 next week. Okay? All right, I'll see you next week.